Hello, this is Professor Melanie Hildebrandt with a lecture on Chapter 6 for our Business Statistics course. Here we're going to look at probability distributions, and it's going to be very similar to what we did in Chapter 3 on relative frequency distributions. But this time we're not describing the past, right? That's what Unit 1 focused on, descriptive statistics. How do we describe what's already happened? Here in Unit 2 in Chapters 5 and 6, we're trying to estimate what's the likelihood that something will occur in the future. I have cut this chapter down a little bit. We're just going to focus on the first 3 learning outcomes on what is a probability distribution, the difference between discrete and random variables, and then the third learning objective on mean, variance, and standard deviation of a probability distribution. We are not doing binomials, hypergeometrics, or Poisson. So just skip through all of those, and we will then move right along. So a probability distribution is just a listing of all the outcomes that, a range of values that could occur based on whatever experiment it is that we're doing. Just like in Chapter 5, a probability of an outcome is going to be between the value of 0 and 1. Our outcomes are mutually exclusive, so if outcome A occurs, that prevents outcome B from occurring. And the list of outcomes that we have, we call it exhaustive. And so if we add up all of our probabilities, then we would get a value equal to 1. As an example, we have a drug manufacturer. They're making a claim that a treatment might cause weight loss for 80% of the population. We could then test the claim using a sample and statistical data to try to see that. So here's an example. We're interested in the number of heads showing face up with 3 tosses of a coin. So we're tossing the coin 3 times. Our outcomes are 0 times there's a head, 1 time, 2 times, or 3 times. So we could just use one of our counting formulas from Chapter 5. We could use the multiplication formula, which gives us the total number of arrangements to expect, right? M times N times ... And so here we're repeating it 3 times. There's 2 different outcomes each time, head or tail. So 2 times 2 times 2. And so we would get 8 possible different outcomes. And then you can see in this chart, we've listed it out here, what would be those 8 different outcomes from doing this experiment. We can then put our probability distribution into a table, and we can even graph the information like in a bar chart. And so you can see again, we toss the coin 3 times. It results in 8 different outcomes. The event of 0 times head showing could happen 1 of 8 is its probability, is 0.125. 1 time was 3 of the 8, as was 2. And then 3 times was only 1 of the 8. And again, if we add all those up, you see that it is mutually exclusive and exhaustive, and our sum of the probabilities does equal 1. So in any experiment of chance, the outcomes occur randomly. So we just call them random variables. Pretty straightforward there. Anything from rolling a dice, the hourly wage of plumbers, the number of runners in Boston marathons. It's all random. We can do random variables, both quantitative ones, or it could be qualitative as well. So some examples, the number of employees absent from the day shift on Monday, the number could be 0 to however many employees we have. And so the number of employees that are absent, that is your random variable. The grade level of the members of the basketball team, right? Grade level would be the random variable here. So the first example is a quantitative random variable, and the second example is a qualitative random variable. So we have 2 types of random variables. Discrete are the result of counting. So this goes back to some of the definitions in Chapter 1. So a random variable that can assume only certain clearly separated values, that's what we're calling a discrete random variable. And so if we toss a coin 3 times and we count the number of heads, if a bank counts the number of credit cards carried by a group of customers, all of those would be examples of this. Now, just because it says that they're clearly separated values, we still could have a discrete random variable. It could still be a fraction or a decimal, but the values must be separated by having some distance between them. And so if we had like retail coupons that were, hey, get 10% off, 15% off, 25% off, those are technically decimal values, right? But there's still separation or distance between those discounted values. So looking more, here's an example then. The Bank of Carolinas counts the number of credit cards carried by a group of customers, and the number of cards they carry is going to be our discrete random variable, okay? And then, so we take the relative frequency of each, add all of it up, and again, we would get to a value of 1. The second kind of random variables we call continuous random variables, and these can have an infinite number of values within a given range. These are typically the result of measuring. So again, discrete was the result of counting. Now it's the result of measuring. These are measured either on an interval or a ratio scale. And the likelihood of a continuous random variable is what's going to be summarized with a probability distribution when we get to chapter 7 in the next unit. But some examples here, the time that it takes a flight to go between Atlanta and Los Angeles, it might be 4.67 hours, 5.13 hours, and so on. So there's a continuous scale of time, okay? Or the annual snowfall in Minneapolis. It's measured in inches. So again, we have a continuous measurement here of the snowfall. So the last thing and the really kind of meat of this chapter that we're going to focus on are mean and variance of a probability distribution. Okay, and so again, going back to an earlier chapter, your mean is just the typical value that we're going to use to represent the centeredness, or the central location of our data. And here our mean is also referred to as the expected value. And so you can see our formula here. Again, this is the lowercase sigma, or excuse me, the lowercase Greek letter mu. And so we would say mu equals, for the mean, the summation of, okay, all of the values in our distribution times their probability, the likelihood that they would happen. We can then measure the spread or variation in the data by using the variance. And so this is sigma squared, and this is where we find the difference from each x and the mean. We square that value, and now this time in this chapter, we're then going to be multiplying by the probability of that value occurring. We can also take the standard deviation, and we do that by just taking the positive square root of the variance. And I'm going to work through an example, or show you an example in just a second here. Okay, and so here is an example. We have this guy, John, and he sells cars for a Ford dealership. And John is actually usually the best salesperson on Saturdays. And so here's his probability distribution for the number of cars he expects to sell on a Saturday. And you can see the highest probability is that he'll sell either 2 or 3 cars with a 0.3 probability here. So we could ask ourselves some questions. Okay, so what kind of distribution is this? Well, it's a discrete probability distribution because there is separation from our values. It's either 0, 1, 2, 3, 4 cars sold. Okay. How many cars does John expect to sell on a typical Saturday? So what's his expected value or his mean? And so remember, the mean of the probability distribution is going to give us a long run average. and we would find that the mean of John's probability distribution is 2.1 cars on a typical Saturday. So over the long run, let's say he works 50 Saturdays in 1 year, then he can expect to sell 50 days times 2.1 cars, 105 cars on Saturdays this next year. And so, that would be his expected value, is 2.1 cars for each Saturday that he works. So now let's look at the variance. And so here's your steps for calculating your variance. You're going to subtract the mean of 2.1 from each value of x, so 0, 1, 2, 3, and 4. You then take that amount and we're going to square it, and then you multiply each squared difference by the probability that that is how many cars John sells. Once we get this last column, we sum them all up, and we arrive at a variance of 1.29. Again, variance is a weird one in terms of units because it's your original unit squared. And so what is a squared car anyway? So we would typically take the standard deviation, and we would find that his standard deviation is 1.136 cars. Maybe we have another employee, and her name is Rita, okay? And we find that she has the same mean. Her expected value is also 2.1 cars on average to be sold each Saturday. But maybe she has a standard deviation of 1.91. So we've got 1.1 for John and 1.9 for Rita. So our conclusion is there's more variability in Rita's sales on Sundays than John's, because 1.9 is a greater amount than 1.1. Okay, I am going to follow this up with another video where I'm actually working through the math steps on some problems here for this chapter.